Section 1.2, Graphs of Equations. In this section, we will define what an equation is. We will use these to sketch graphs, and then we'll look at various properties of graphs, such as the x and y intercepts, and we'll see what it means for a graph to have symmetry, and then we'll look at an application to finish it off. So let's begin by defining equations. So what is an equation? For us, an equation has an equal sign and is a true statement. And these can be simple. These can be something like 2 is equal to 2. Or, as we've seen before, x is equal to 2, if we want to get a little bit fancy and throw in some variables. But for our purposes, we will be using two variables. X and y. And an example of an equation with two variables is the following. Y is equal to 2x plus 3. Again, we have this equal sign making an equation, but what this means is a little bit more mysterious than x is equal to 2. So first of all, normally, we let y be on one side of the equation, and we plug in values for x. So for example, maybe we say x is equal to 1, then y is equal to 2 times 1 plus 3. Here, we've taken the x from the equation and substituted in a 1, and we can see that y should be 2 plus 3, which is equal to 5. If x is equal to 1 and y is equal to 5, this is a true statement, and it is a solution to the equation. So what does it mean to be a solution? Well, we'll write down a definition. Given an equation, make it a little nicer, an ordered pair is a solution if when we let x be some value a and y be some value b, the equation is still true. So if we go back to our example here, the ordered pair 1, 5 is a solution to y is equal to 2x plus 3. And the takeaway word here is solution. And again, this is because if we plug in 1 for x and 5 for y, then we saw we had the statement 5 is equal to 5, which is obviously true. On the other hand, 1, 3 is not a solution to y is equal to 2x plus 3, since if we plug in 1 for x and 3 for y, we see we get 3 is equal to 5, which is definitely false. Okay. So why do we care about the idea of solutions? Well, this is where the idea of graphing comes in. And if we want to look at a graph, what we're really looking at is the set of all solutions to a given equation. We call this the solution set for the equation, or the graph of the equation. And the takeaway word here is not only solution set, but in particular the word graph. A graph is a pictorial representation of all solutions to any given function. And this might seem a little bit intimidating. And that's because an equation with two variables has infinitely many solutions. If we go back to our example of y is equal to 2x plus 3, we saw 1, 5 is a solution. But if we let x equal 0 and y equal 3, we have another point that's a solution. As a matter of fact, we could let x equal negative 1 and y equal 1 and get yet another solution. So how do we take this infinitely many collection and make them something that we can look at and use? And we do this with the basic method for graphing. With this method, we'll be able to take any equation and turn it into something that we can actually look at and use instead of just talk about theoretically all these infinitely many solutions. So there are 4 steps here. The first one is isolate y, or in other words, get y by itself. As we saw in y is equal to 2x plus 3, that's already done, and in a lot of examples it'll be done too. Once y is by itself, the second point is to construct a table of values where we pick x values and find their y values that make the equation hold. Exactly as we did above, when we plugged in x is equal to 1 and saw y had to be 5. We just want to do this for a couple points to sort of see what the shape is going to look like. Once we have this table, the next step is to plot these ordered pairs on the Cartesian plane. And finally, connect the points with a smooth curve. So let's do this and actually plot the graph of y is equal to 2x plus 3. Okay, so y is by itself, so step 1 is taken care of. The next step is just pick some x values and find their y values. And to do that, normally we make a nice little chart with x on one side and y on the other. and we pick small x values, such as -2, -1, 0, 1, 2, and then find the y values that make them hold. What this means is we take -2, for example, we plug it into our equation, and we see what y must be. 2 times -2 is -4, plus 3 is -1. And we write down -1 in the y column. And we do the same thing now with each of these values. Here, x is equal to -1. So this is -2 plus 3, which is equal to 1. And then we write down 1 there. And now on your own, make sure you can get the rest of these y values here. And I'll write them down. And if you didn't get these, ask questions or double check your work to see what went on. And now we're done with step 2. Step 2 is where most of the work happens. Step 3 and step 4 are easy by comparison. In step 3, we write down a nice Cartesian plane here. And like always, we give it a couple points to sort of get our bearing on here. And we see we'll need to use some high y values here. So let's mark up to 7. And then we just plot them down. If x is equal to -2, y is equal to -1. So we put that point down. If x is equal to -1, y is equal to 1. So there's our next point. X is equal to 0, y is equal to 3, 1, 5, 2, 7. And what step 4 says is just connect these in the way that makes the most sense. So we draw a nice line between them. And we extend it off past -2 and 2 because the solution set actually goes forever. And now we actually see a visual representation of what this graph should look like. What are the actual solutions here? And we use this a lot in a wide number of fields if we want to see sort of how things are changing over time and get a good estimation beyond data points that we already have. Now, what else can we do with a graph? Well, some points might be standing out to you here. Maybe we want to know when it hits the y-axis here, or on the other hand, maybe we want to know when it hits the x-axis. This could be good information. For example, if the x-axis represents time and the y-axis represents money, we might want to know how much money we start with when time is 0. That would be, I don't know, $3. Or on the other hand, we might want to know when we run out of money and we hit the x-axis there, which happens at about a little past -1. And we can look at the graph and figure out where these points are easily, but what if we actually want to solve for them? And we'll do that next. And we'll give these points names. We call these the intercepts of the graph. So again, to write down sort of a nice definition here, these are the ordered pairs that hit the x-axis and the y-axis. And we call them the x-intercept and the y-intercept. What points intercept the axes? When are we passing through them? So the takeaway word here is x-intercept and y-intercept. And now let's talk about how we can actually find them. And it's actually quite easy. So how do we find them? And let's talk about the x-intercept first. Note that if we look at our graph up above here, to be an x-intercept, we need to be hitting the x-axis, meaning y has to be equal to 0. So we set y equal to 0 and solve for x. So we'll do this for our example of y is equal to 2x plus 3. The only rule, set y equal to 0, and then get x by itself. So first we'll subtract 3 from both sides, and then we'll divide by 2, and we have the x value. So, negative 3 halves, 0, is our solution, that is our x-intercept. Finding the y-intercept is equally as easy. Now, we just set x equal to 0 and solve for y. And we'll do that real quick with our example. Y is equal to 2x plus 3. Set x equals 0. Y is equal to 2 times 0 plus 3. 0 times anything is 0. So y is equal to 3. And our ordered pair, that is the y-intercept, is 0, 3. So remember here, for the x-intercept, y is always 0, and for the y-intercept, x is always 0. If we remember that, they're quite easy to find. And we'll see more uses of these as time goes on. For now, we're just introducing the idea, and so we'll move on to symmetry. So the symmetry of a graph is exactly what you think it would be. The symmetry of a graph will be places that make the graph look like it was reflected in a mirror. We'll ignore that weird black line on the side there. Let's get rid of it. Well, there we go. So the name is exactly what you think it would be like in the real world. And there are 3 types of symmetry that we'll talk about. And they're easy to remember. The first one is x-axis symmetry. And these are graphs that make the x-axis look like a mirror. So it would look something like this, maybe. You can see we sort of have 2 pieces here. We have this top piece, we have this bottom piece. And for it to have x-axis symmetry, these 2 need to be exact copies of each other, just flipped over the x-axis. Meaning, if we pick some x value here, let's just say this is x, then a point on the graph, xy, should have a mirror image of x negative y below it. Whatever our y value is, it just sort of gets flipped to the negative direction, and we have both those points. So the test for x-axis symmetry is a graph has x-axis symmetry if for any solution xy, then we also have x negative y as a solution. We see that while x remains fixed, the y's sort of can flip-flop between being positive and negative, and there'll still be solutions for our graph. The next type of symmetry we'll talk about is very closely related, but now we're looking at y-axis symmetry. Here, the y-axis looks like a mirror, and so we can have an example as such here. Again, we have two pieces, and each one sort of looks like it's just been flipped over the y-axis. And so we have a similar sort of test here. If we pick any y value, maybe we'll call this point here xy, then we can travel along the same y value and hit the opposite point, negative xy, on the other side. So we have to have both these points here. And you see it's very close to x-axis symmetry, just with the roles of x and y reversed. So we can write a similar type of rule here. A graph has y-axis symmetry if for any solution xy, then negative xy is also a solution. Here, it's a y-axis symmetry, so the y stays fixed, and we're allowed to flip-flop the x back and forth. The final type of symmetry is a little bit trickier, and this is called origin symmetry. And for us, the origin corresponds to the ordered pair 0, 0, where the two number lines intersect. And really, this is a special case of symmetry. It's a little bit harder to see at first. So let's draw an example, and then we'll talk about how we can recognize it. So I claim the following graph has origin symmetry. This graph, it looks sort of like a funky S here. And what it means to have origin symmetry is we can sort of see this correspondence, but both x and y are changing here. So let's grab a point, maybe right here, and we'll just call it xy. Now, not only do we want x or y to change, but we want both x and y to change. So if xy is a solution, then we should be able to look on our graph and see that negative x, negative y is also a solution. So it sort of tells us a path we can take. If I can follow this up and over to xy and get a solution, then I should be able to go backwards and sort of reverse the steps to get down to negative x, negative y, and still be on the graph. And once we know the rule, writing it down is still quite easy. You can see I haven't checked my email for the day. So we'll write down here. How about in black? A graph has origin symmetry if for any solution xy, we also have negative x, negative y is a solution. Again, we have this mirroring process, but it's a little bit stranger. Not only do we need x and y to sort of be defined here, but we need both of them to flip very rigidly. It can't just be one or the other. It has to be both x and y changing to be negative. And these are easy because they allow us to graph functions without worrying too much. For example, if I know that a graph has y-axis symmetry, and it looks like this, then the other side is already set in stone. It has to be a mirror image that copies it verbatim, so that we have these nice lining up of points here, which we sort of have on this sketch. And we can see some use here, and we'll talk more about different kinds of symmetry when we get into functions. So for now, as long as we remember our three types here, why don't we underline them? Our x-axis symmetry that says if I swap y and make it negative, I should have the same x value. Our y-axis symmetry, which says the opposite. If I swap x and make it negative, I have the same y value. And our origin symmetry, which says if I swap both x and y, then I should still be a solution. Knowing what these are and storing them away is good enough for now. So why don't we end by looking at a nice way to tell when our graphs have these types of symmetry. So we have three types of symmetry, so we'll have 3 points here. We can see if a graph has x-axis symmetry, if replacing y with negative y yields the same equation. Okay, so to see an example of this, let's say we had y squared is equal to 2x plus 3. If now I take negative y and I square it, then negative y times negative y is positive y squared, which is equal to 2x plus 3. And after we made the change and simplified, we ended up with the same equation on both sides. We'll see that actually x-axis symmetry is something we want to avoid, and it looks a little bit weird here. We had to square the y instead of trying to simplify and solve for the y. Secondly, a graph has y-axis symmetry if replacing x with negative x yields the same equation. And again, we'll use a nice example here. Y is equal to x squared plus 1, same game. Make this x a negative x, and then square it. That's a 1. And this gives us y is equal to positive x squared again. And we have the same sort of a relationship here. Once we simplified, we ended up with the same equation. And the reason why I use a square in both examples is not anything tricky, but it is important. And finally, a graph has origin symmetry if replacing both x with negative x and y with negative y. Well, let's make this a little more y-y. There we go. Yields the same equation. Again, with origin, we need to change both x and y, and it always has to be both of x and y. So now we have some nice formulas we can use to check if it has symmetry algebraically. And that will finish up section 1.2.